So this last sort of bonus section is about a category of compounds called hydrates. The reason why we're talking about this now, it's got to go somewhere. It could have gone in ionic compounds, but we will do our lab for this chapter concerning hydrates. So we really need to learn it now. So what are hydrates? As the name implies, hydrates has something to do with water. And the idea is that, when we have solid ionic compounds like that I get from a chemical company in a jar. You've seen them. They look like just white chemicals, right? Like, granular. They look like salt. Everything kind of looks like salt. And they don't look wet at all. They look like solids. They look dry. What oftentimes is true is that they are what we call hydrates, which means that inside their crystal lattice, there is hiding some water molecules. So, if you think of this ionic compound, here would be Na, here would be the SO4 2- polyatomic ion, and then here would be another, SO4 2-. Here would be maybe an Na, and then inside this area right in here, maybe there's some water molecules hiding out. And it could be 2 or 3 or 4. And how we define it is how many per formula unit of the ionic compound. So first of all, these are only ionic compounds. These are when you have water molecules trapped inside ionic compounds. And as you can imagine, here I have the hydrate, sodium sulfate, with 10 water molecules in between the ions, and I have 10 of them for every 1 formula unit of sodium sulfate. And you can imagine that if I were to heat this compound up, that we know ionic compounds have really, really high melting and boiling points. But water, we know, evaporates at 100 degrees Celsius, becomes a gas at 100 degrees Celsius. So if I heat this up, look at what has happened. The red are the water molecules in this diagram. And you can see the water molecules have become a gas, and we are left with the sodium sulfate without the water. So the word without water is anhydrous. So this is a hydrate. Hydrate is with water, and anhydrous is without water. So most of the chemicals in that back storage room in between my room and Mr. Marsh's room, most of the chemicals in there are actually hydrates. This is not something that is uncommon. You can see a lot of maybe chemicals that we have used before. Some we used calcium chloride, we used sodium carbonate, we've used both of those in various labs. So you can see that we have different numbers of hydrates, right? That's how many waters there are per formula unit of the ionic compound. And how we give a name for that is we use mono, di, tri, tetra, depending on how many water molecules there are. How we symbolize that is we have the ionic compounds formula and then dot, and then the number of H2O. It's like a dot. It's not a period. It's a dot sort of in the middle of the two, where the bottom line is and the top line is. And so what we will do in the lab and what we're going to do here in the practice problem is figure out what is it a monohydrate, a dihydrate, a trihydrate? Figure out how many, the wording that we use is waters of hydration, how many waters of hydration there are per formula unit of the ionic compound. So what's really important when doing these problems is labeling or understanding what each of these numbers is representing. So when I read this problem, an 11.75 gram sample of a common hydrate of cobalt 2 chloride is heated. So this right here, this 11.75, it says the word hydrate. So that means 11.75 grams is with the water, right? It's cobalt 2 chloride with water. After heating, 9.11 grams of anhydrous cobalt 2 chloride remains. So this is telling me that 9.11 grams of just the cobalt chloride, but right, without the water. And the question, what is the formula in the name of the hydrate? So essentially what I want to do is I want to find out, well, how many moles of water are there per moles of the actual compound, right? If I go back to this, that's what this table was showing me. 4 moles of water for every 1 mole of iron 3 phosphate. 5 moles of water for every 1 mole of copper 2 sulfate. So I need to figure that out. So I need to find moles of water and moles of the compound. If I read this, I don't actually know the moles of the water yet. But I always know that the mass of the hydrate will be equal to the mass of the anhydrous compound plus the mass of the water, right? If I go back to this, right, the mass of the hydrate would be equal to the mass of the compound plus the mass of the water. Think about, like, these are sealed containers, right? So the masses would be the same on both sides. It's just where are the water molecules. So the mass of the hydrate was 11.75 grams. The mass of the anhydrous compound was 9.11 grams. And if I subtract 9.11 grams from each side, I get 2.64 grams is equal to the mass of the water. I don't need the mass of the water, I need the moles of the water. So I take 2.64 grams of the water and I convert to moles using the molar mass of the water. And I get 0.1465. So I know that's going to be the top. And now the mass of the anhydrous compound, this 9.11 grams, that was the cobalt 2 chloride, COCl2. I convert that. So I divide by the molar mass of the cobalt 2 chloride, which is 129.83 grams. And so the moles of that is 0.0701. So it's the moles of the water divided by the moles of the compound. And when I divide those two, I get the number 2. What does that tell me? That tells me that my formula is COCl2 dot 2 H2O, right? It's telling me 2 water molecules for every 1 cobalt 2 chloride, which will mean the name of this compound is cobalt, Roman numeral 2, chloride, di for 2, hydrate. So you have a few of these on your homework, and then of course this will be what our lab is. Basically your lab, I'm going to give you a sample of a hydrate and you're going to do this. You're going to figure out how many waters there are.